All right, so units are just as important as numbers when we do the math and to look at the quantity of chemistry. All right, and so how many basic units are there? Do you remember? Yes, 7. I saw that in the back. Okay, and they consist of a whole bunch of things. Go back real quick. Maybe, real quick. Oh, where were those units? Wow, there they are. Very fast. Kilogram for mass, meter for length, second for time, Kelvin for temperature, mole for the amount of something or a number of things, and then the last two, ampere or electricity, will be in GChem 2, and candela will be in physics. Okay. And so what we're going to do is, that isn't the only units that we use in chemistry. We have a whole set of units that are what are called derived. They are combinations of the basic units to create a new unit that is important to us. And the first unit that we talked about that was derived, or a unit that was based on others, was volume. And so when you looked at those basic 7 units, and you couldn't go in and buy a 2-liter because we didn't define what a liter was. We understand that it's volume, but it is not one of the base scientific measurements. And so there's a whole bunch of units, and we will define units as we go from chapter to chapter to chapter as we start looking at new things. And so some things that you might understand and are familiar with: volume. You may have heard about density, probably through physical science and through chemistry. Speed, acceleration, these are all combinations of the basic units. And so we'll introduce different ones as we get there. And so when we take a look at units, there are some ones that you probably need to know straight up right now. Area is a length times a length, and if the base unit is meter, then that is meter times meter. Volume is length times width times height, all measured in a distance, and so that is meter, so it's meter cubed is the base unit. Density is mass divided by volume, and so we now are using a base unit kilogram divided by a derived unit volume to get a secondary derived unit density. So this can go down the rabbit hole in terms of combining lots and lots of units. Speed is meters per second. Accelerations, meters per second squared. Then we get into really fun things. We get into combinations of units that are so complex that us lazy chemists and scientists don't want to write it all, so we'll substitute something for it. So force is a kilogram times a meter divided by a second squared. And what we're going to use for that is we're going to use Newton and say Newton is exactly this base unit because it's just so complex. Pressure, Pascal, we can see is a combination of several units. And energy, which we use as a joule, is another. Now, if you take a look at force, pressure, and energy, they are very similar. They use the same things. They use a kilogram, a meter, and a second, but the way that we combine them and how many we use of them creates totally different units. And so a Newton, a Pascal, and a joule will be force, pressure, and energy. Now, sometimes we'll need to get into those units to understand what we're doing. Sometimes you just have to know that energy is a joule, and we will spend an entire chapter on energy itself and delve into that. But what I want you to know is that there are derived units, and we'll introduce those as we do more calculations. The ones that we're going to really use in this chapter, or this unit, is area, volume, density, and speed. Those are the ones that we're going to kind of focus in, the very simple ones, and then we'll go on and use the others later. Now, volume. The base unit for volume is meter times a meter times a meter. And so I don't have a meter stick here, but let's think about this. Meter, about this big. By a meter, about that big. By a meter, by about that big. You would have a box like this. Now, even when you get a drink at the theater, it's not this big. Okay? Theater drinks are huge, right? But this is way too big. Could you pick up a meter times a meter times a meter full of Coke, a container? No. That is unusable. Even though it is the definitional unit, it's just too large. And if we go into the laboratory, we never measure anything in that particular unit. So we derive or we define a unit that is much better or smaller, that is more effective for us to use. And so for the volume, what we're going to do instead of using a meter, what we are going to use is a centimeter. Okay? How many centimeters make up a meter? 100. It's 100th. So instead of this big unit, we're going to use a unit that's about that big. Okay, if we have a volume this big by that big by this big, could you pick up a container of water that size? Yeah. That is a reasonable amount. Now, the cubic centimeter, okay, centimeter cubed, okay, one of those, all right, can be rewritten. And in older things, if you've watched a television show that is medically based and someone needs a shot, give them 5 cc's of adrenaline, okay? cc is another terminology for cubic centimeter, okay? So that unit is exactly the same as writing centimeter cubed at the top. But we're going to define the cubic centimeter in terms of something that you understand about volume. We're going to define it in terms of a liter, but we're going to define it in terms that it is 1 milliliter. Okay? This is where we get to liters themselves. It's through this conversion. 1 cubic centimeter is the same as 1 milliliter. That's where that definition comes from. And so if we have 1,000 of those milliliters, you have a liter. And if you have 2,000 of those, you've got your 2-liter bottle of Coke. So this is where that comes into. And what we're doing in terms of volume, it is a cubic measurement, and we use the derived unit liter most often. So we'll talk about liters, we'll talk about milliliters, because that is very easy to measure in laboratory. Another unit that is defined has something to do with water, okay? And so the density is the mass divided by the volume. And what we want to do is, density is kind of a ratio. So we need something to reference it to. And what we do is we reference it to water. Okay? And we know that the density of water, if I take 1 milliliter, which is the same as saying 1 centimeter cubed, all right? And we made a definition. The actual amount of water that makes up 1 milliliter, we define as 1 gram. This is where mass comes from. And so the density of water, if you take 1 divided by 1, you get, all right, didn't even pull out your calculators, 1. That's great. The density of water is 1. This is definitional. This is everything by which we compare. If by chance something has a density that is greater than 1, if I throw it in a pool, what will happen? It'll sink. If it has a density that is less than 1, what will happen? It'll float. Okay, and that's the kind of thing that we compare. Now, Very often, most things are very dense, okay, like most of the elements that we have on the periodic table are denser than water, and so they would sink, but there are things that are less dense, and we use this as a reference. Now, why in the world do we have density? We use density to identify something. It is a unique property of that particular compound element itself. And so if I go into lab and I find a liquid and you've left it on the table, you didn't mark what it is, okay, one way I can identify what it is I can take the volume, measure it, measure the mass, calculate the density, and based upon that number, you can go back and calculate what or reference what that item might actually be. Okay? And so that is how we're going to use density. Now, let me show you something real quick. When you look at your CHEM-111, and I'm going to go down to problem number 18. Okay? All right. Check this out. Problem number 18. A chemical was found on the lab bench that was not labeled. Its mass, okay, its mass is right over here, 0.663 ounces. Stop. Okay, so that's the mass. And its volume is 5.24 e to the minus 3 gallons. All right. And you have this list of densities. What do you think you're going to do with this particular problem? Well, density, I said, was what over what? Mass over volume. And so I have a mass in ounces and I have a volume in gallons, so I could take that number, mass divided by volume, gallons, and I have a density, right? Does that help me at all? The number that comes out will have a unit of what? Ounces per gallon. And that's a valid number. It would be right. But what is my reference list in? Grams per milliliter. So even though I can identify a mass and I can identify a volume and I can make a density, sometimes the numbers you're given aren't exactly the numbers that you need to complete the problem. All right, and so we're going to have to change some of these units that are given into things that we need so that we can solve the problem. But you have a problem about density, and so when I taught you density, I defined it, right? I defined what it was. But here's a problem that references density. That isn't as straightforward, is it? It gives you a scenario, it gives you mass, it gives you volume, and it wants you to do something with it. And so sometimes I will define something, that density is mass per volume, and then I'll give you something a little bit more complex to apply what that actually means. Okay. And so here's the problem. One way with density. Sometimes we don't reference it right. So what weighs more? A ton of bricks or a ton of feathers? They weigh exactly the same. But when you think about bricks and you think about feathers, which one has more volume? You have to have a boatload of feathers to get up to a ton. How many bricks do you really need to get to a ton? Not really that much. What we're thinking about in terms of comparing those two, they are different, not in weight, they are both weigh a ton, but in terms of density, there is a very different density between the two things. And so sometimes we think about mass, weight, and density all as being one thing, but it isn't. We have to understand that mass, weight, and densities are slightly different and used slightly differently. Now, in that problem before, we gave you ounces in mass and gallons in volume, but those were not the units we needed to finish this problem. And so we're going to use a mathematical tool to calculate or convert numbers into things that we need. And so we're going to give you numbers to use mathematically. And unfortunately, it probably will not be the number that you really need. Okay? Like we need mass in grams, so we obviously give it to you in ounces. Okay? And we give you a volume in gallons, but we really need it in milliliters. Now we do that to have you practice. Okay? We're not just being mean. It feels like it, I understand. But we want you to practice this. And so the strategy by which we are going to make you convert these things is to know conversion factors. Okay? What we need is things that are equal to each other so that we can convert from one unit to the next. Okay? Well, what is a conversion factor? Okay, gallons, let's say. What can you convert gallons into? Let's say quarts. How many quarts make up 1 gallon? 4 quarts make up 1 gallon. And so I have a conversion factor now that says 1 gallon is equal to 4 quarts. The amount of a gallon, the actual physical volume of a gallon, and the actual physical volume of 4 quarts is exactly the same. Something on top is the same, something on the bottom is the same. I divide it out, that is equal to 1. If you multiply any number times 1, do you change the number? No. I'm going to multiply by conversion factors, which are essentially 1. I'm not going to change what that number means. I may change its value, but I'm not going to change what that number represents by using conversion factors. And so I can change the number of 1 gallon into 4 quarts. That number has changed, but what it means, the actual volume, hasn't changed at all. I've just defined it in a different way. And so to calculate things, what we're going to do is we're going to first identify what is given. That should be easy. You read the problem and you identify what's given. Okay? Second, we're going to identify what we want at the end. That one is a little bit harder sometimes. Now, the problem may tell you exactly what you want it to be in. Okay? But the problem that I showed you about the density, I gave you mass in ounces. I didn't actually tell you straight up what I wanted, but I gave you a list of densities in grams per milliliter. And so to make any reference, I had to convert the ounces of mass into grams of mass to figure that particular problem out. So you have to decide where you want to end up. Third, you have to have enough conversion factors to complete the process. Okay? Conversion factors come from 2 places. 1, you memorize them. So that's a big list. And I'll show you a list of that. There's a page on CHEM-111 in the reference section that gives you lists of conversion factors. Second, in the problem, sometimes the problem will define a brand new conversion factor for you to use. And it has to be used to solve what you need. So you're going to have a base of conversion factors that you know, understand, is in your heart of hearts, and you'll know for the rest of your life, or at least to the first exam. Okay? And then to the second exam, because you got to use them again. But there are some conversion factors that we're going to give you. Now here is the thinking problem. What happens when the problem gives you 2 numbers? One is the beginning unit, and one is a conversion factor. You have to decide which one to use. And you have to distinguish between, is this a conversion factor, or is this the beginning given factor? That requires a little bit of thinking. And so You need to be careful about identifying what you're given, where you want to go, and if there are conversion factors that are given or are there conversion factors that you have to memorize. All right. If I go to the chemistry reference and I actually click common chemical conversion factors, okay, we see a bunch of them. And so things that you probably, I assumed you knew even before you walked in here. In 1 foot, there are 12 ounces. I mean, in 1 foot, there are 12 inches. That's 1 foot, there's 12 ounces. That's interesting. Okay. I assumed you know that there are 3 feet in 1 yard. I assume that you know that in 1 mile there are 5,280 feet. You may not have known this one. 1 mile is 1,760 yards. But most of that I felt you should know. If you've ever cooked, you should know some of these. 8 ounces in a cup, 32 ounces in a quart, 2 cups in a pint. Okay, these are things that you can look at. Oh, this is great. This is where English units really don't work real well. We see ounces as volume. We also see ounces as pounds. 16 ounces is equal to 1 pound. We really, in the English system, have messed things up. We confuse ourselves. 2,000 pounds is 1 ton. Okay. And so we've got that. We've already asked you to learn a list of all of the prefixes. And so let's say 1 milliliter is 1 times e to the minus 3 liters. So that's there. And then there are a couple of special ones that we're going to use. But I really want to identify the 3 that we need. All right, this one right here. All right, centimeter to inches. Very important. That is the one that converts length that is in English measurements to lengths that are in metric measurements. So that's a key. The other one is volume. The quarts to liters is how we change English volumes into metric volumes. And then pounds to grams is where we convert English mass into metric mass. Those 3 should be ones that you should really understand, okay, and know, and you need to know this particular number. All right, I'm going to give you a heads up about Chem-111. It is picky. You have to be exactly right for it to count correctly. Okay, so if you put in 1.056 quarts equals 1 liter, it's going to be totally wrong. Okay, because it is 1.057. Even if you find a reference tool somewhere on the internet that did say that quarts is 1.056, this is the reference point that it's going to use in that homework, so use this reference tool. Okay. And so, common conversion factors, after you've done some of this homework, you'll memorize more than you think. Okay? And so, let me try this. All right. All right. So let's try some of these. All right. So Let's try a few. Oh. How many eggs are in 3 dozen? Okay. Now, most of us can do this one in our head, right? But write down on your sheet how you would mathematically show someone that 3 dozen eggs is what you can calculate in your head. And I've got that conversion factor thing sitting in the wrong place. Okay. Feel comfortable about that? Let me show you how I would do this. First, identify what is given. What is given? What is the unit that is given? 3 dozen. So, dozen is what I'm given as the unit. The numerical value is 3. Second, what do I want it to end up being? Eggs, number of eggs. Okay. And so, I now know what I start and what I'm finishing. I need to know a conversion factor. What is the conversion factor that I use for this? 1 dozen equals how many? How many? 12. Now, the first part of the math, dozen divided by dozen is 1, so we talk about it canceling out. What unit am I left with? I'm left with eggs. And if you pull out your iPhones, that is what number? 36. Oh, great. All right. In the next question, it says, starting with that 3 dozen, if one person can eat 2 eggs, how many people can eat? Okay. What is the additional step here? What information do you get from that next line? 1 person over 2 eggs. You get a brand new conversion factor. You would have never known that. I had to define it because obviously there's lots of people who can eat lots and lots of different eggs, but in this we're going to define that. And so if I start with my 3 dozen, again, I've already converted the dozen into eggs. Okay, and now we say this. We know there is a conversion between eggs and people. People is what we want at the end. And that conversion factor, in this case, we now know that the units are right because dozens cancel out and eggs cancel out and I'm left with people. But the numerical value, what goes with what? What number goes with people? 1. And what number goes with eggs? 2. And mathematically, 3 times 12. I can divide it by 1. Do I have to divide it by 1? No. Times 1. Do I have to multiply it times 1? No. Divided by 2 is equal to what? How many people can eat? All right. Okay, not too bad. A little bit more complicated. How many seconds are there in 1 hour? And then work with a partner to check your work. Find out how many seconds are in exactly 1 year. That second question is just going to have a little bit more steps. As you look at that, I assume you know some conversion factors about this. How many seconds are in a minute? 60. Good. Whoa. Man. How many minutes are in an hour? 60. Great. So you got this, right? How many hours are in a day? Not enough. 24, yes. Okay. You're heading in the right direction. Oh, a good thing from this point on in the semester, bring your calculator. Have it on the desk at all times. Because we do lots and lots of calculations with lots and lots of things. Here's one thing about the year problem. There's not one single way to solve it. Okay? There could be multiple ways that get to the same place. All depending upon how the relationships that you know and how to get there. Okay, when you get done, check your work with the neighbor. Hopefully, your neighbor is getting an A, so you can trust them. If you have differences, figure out why. Where's your start? No. You're doing, I had these. Yeah, you're going to need the other sheet. Sorry. All right. Yep. Okay. So, if I start off with this, in the first one, what is the unit that I am given? In the first here, how many seconds are in? The unit that's given is 1 hour. Okay. Now, 1 hour, the unit is hour 1. Where am I heading? What unit? Seconds. To seconds. Okay, so that's where I'm heading. Now, can I change hours to seconds? Do you know a conversion that goes directly from hours to seconds? Do you know it off the top of your head? What is the thing about hours that you know right off the top of your head very quickly? In 1 hour, they're what? 60 minutes. Now, that doesn't seem like I've solved the problem, but it gets it one step closer. Ah, bugger. Totally lost it. All my work. Okay, 1 hour times in 1 hour, there are 60 minutes. Because I have a conversion factor in my head that can change minutes into what? Seconds. And that conversion factor is what? In 1 minute, how many seconds are there? 60. Okay, there are 2 things to check when you do these problems. to make sure you get this right. Hour on top, hour on bottom. Cancel, or they divide to equal 1. Minutes, I'm left with the only unit left is seconds, correct? The other thing that you have to watch out for is to make sure that the numbers go with the correct item. 1 hour is 60 minutes. 1 minute is 60 seconds. If I put 60 here and 1 there, the units are set up right, but the numbers are not. And so if I take 1 times 60, what is the number that you get out in the calculator? What was it? 3,600. Is that the correct answer? Hmm?
36 seconds per hour.
Well, 36 seconds in terms of how many seconds is not, well, you can say it's per hour, that's correct, but the answer I wanted was in seconds. But if you put this into the CHEM-111, it's going to mark it wrong. Why? Sig figs. How many significant figures do you, when you write 3,600, how many sig figs are there? 2. Could be 2, could be 3, or could be 4. Okay? And so how would I write this correctly? 3. Oh, that's an ugly 3. 3.60. And then what I would write? Times 10 to the 3. All right. Or in CHEM-111, I write E to the 3 seconds. Writing E, and in most of your calculators, it'll say E also is times 10. Okay. All right. The next is just a little bit longer. The unit I start off with is year, and I want to change that into seconds, so I start off with 1 year. What is the easiest thing that I know of about converting years? What is the thing that you know years can be converted into? Days. All right, and what is the numerical equivalency? 365 days is in 1 year. Times. Okay, what can you convert days into very quickly? Hours. Days into hours. Numerically, what are those? 24 hours in every 1 day.
Hey, Dr. D.
Yes.
So in GeoB Chem, I think we started smaller and went bigger. Do we need to go bigger and then go smaller on these?
Start smaller.
So we started with seconds and went up to years.
In this case, we are going to, I would like you to start with the not larger, just what is given as the definition, and then head towards where you need to go. And so what was given here was a value of years, and then we're going to go that direction. All right? Now, have I finished? If I stop the problem now? No. Now, what can I change? What is the next step? Hours can be changed into what? Okay? At this moment in time, the one that you know off the top of your head is 2 minutes, but because of the last problem, you know that you could have used hours to seconds because you just calculated that, but just going on what you probably know in your heart of hearts right now, I would say 1 hour is 60 minutes, and then I'm almost there, right? Minutes can be changed into what? Seconds. And 1 minute is 60 seconds. Okay, and so we have seconds. What came out in the calculator? 31,536,000, and that's it? 0. All right. If you put that into the into CHEM-111, what is it going to say? Wrong. All right. So what do? Sig figs. How many sig figs? 3. So come on. 3.15 E, or times 10 to the Yes, 1, 2, 3, 4, 5, 6, 7 seconds. Yep.
We're not need to, for sig figs that we're doing.
Oh, wait a minute. Did we get sig figs? Okay, so in this, we have to go to 1, 2, 3 sig figs. So 1, 2, 3. 3.15. The next number is a 3. And so the number, since 5, the next number is 3, we round down. Okay, so 3.15 e to the 7th seconds. Okay. All right. The last one I want you to do is to take a look at, oh, here we go. Units can be given everywhere. And so here's a problem. I was looking up a unit and I found this unit. It's called the butts. It is equal to 126 gallons is 1 butts. So I thought of this problem. In an Olympic-sized pool, you have 1,000,000 gallons of water. How many butts would it take to fill that pool? Okay. My given unit is 1,000,000 gallons. All right. Now, this is not a unit that you know of, but it can be given in the problem. It says 126 gallons is 1 butts. So how many butts does it take? Okay. Pull out my handy dandy calculator. 1,000,000 divided by 126 equals 7,936.50794. That's what came out of the calculator. So basically it takes 7,936 and a half butts to fill the pool. All right, so what is half a butt? Give it to me. A cheek. No, that is not an official unit, but this would be, you can be given, I use this, you can be given a new conversion factor just in the problem alone. All right? Okay. There are a couple things that we need to look at conversion factors next time. We're going to complicate it a little bit. We're going to start converting both two factors, one on the top, one on the bottom. We are also going to start doing volumes and areas, which I want to make sure that you are very careful about how you put it into the calculator, and then some strategies. But at this moment in time, you should be able to attempt all of the problems in Chem 21. Please look at the tutorial about how to use the dimensional analysis math. If you watch that video, you should be able to do all the problems that are asked of you at this moment in time. So start on them, okay?